Okay, so now the last topic on capacitors is basically looking at what happens when we start hooking capacitors up, more than one capacitor. And there's two ways that we can do it, in series and then in parallel. And so what we're looking at right here, you can ignore this bottom figure, I'll talk about that in a little bit. But this is called in series. So I have two capacitors, and we would say that they're hooked up in series. So what that means is that they come one right after another. So as we go around a circuit, which is what this is, a loop like this connected to a power supply, as I come around, once I pass through one, I have to pass through the other one. If that's what's going on, then we say that those are in series. We'll talk about in parallel in a little while. So we can imagine kind of what's happening in slow motion, because remember this happens very, very big. Oh, so also I marked 3 points, A, B, and C, just indicating that the potential difference, but I'll come back to this. We just want to think about what happens, once we connect to the battery. So once the battery is connected, this is a positive potential on this side. And so what that's going to do is it's going to start pulling electrons off of this side. And so the electrons are going to come flying off this plate, leaving like a positive here. And so, eventually they'll come around and that one's going to be planted on this side, right? Okay, so if I were thinking of the field that's generated just by this little bit of charge, okay, it's not the full charge, it's not done charging. The electric field here is going to be, in this direction, and from this negative is also in this direction. And so what it's going to end up doing is pushing off a charge here. And so this charge then this electron would be pushed off this plate and come up here and land, which would leave a positive here, and then it's going to happen all over again. So we'd pull one off here, and it's going to whip around and land here, and push one off here, which will come over here, and so on. And so we keep getting this buildup. And what we see is because of this process, once it stops, whatever charge is here has to be the same down here. So we would say that, if this charge is positive Q, then I'm going to have the same exact charge down here. And that's true. So in series, capacitors have the same Q, the same charge. They have the same charge. And that's important. Okay. The second thing that we want to think about is a potential difference means that, remember a change, so that's change in potential. So that would be the final minus the initial. So if I imagine from A to C, which is the same as like across the battery, 12 volts. If my change is a total of 12, then basically I have to go from 12 volts, to 0 volts, or other way around. It doesn't matter where I put my 0, but that's a drop of 12 volts. So now we can think about the potential across each of these. And what we should see is that as we drop down over this, whatever this one is, we'll call it delta V1, and this one, delta V2, these are not the same, don't have to be, they could be, but whatever they are, they have to add up to be 12. It has to be the total, because I got to go from 12 to 0. So if I drop 6 here, I got to be 6 here. If I drop 5 here, then it would have to be 7 here. And so we can write that out. And so we'll say that the total potential difference is equal to V1 delta V1 plus delta V2. By the way, just going forward, if we just write V, that's fine. So for going forward, potential difference, if you want, we can just say that's V. It just helps with the notation, so we don't have to write these deltas all the time. So if I multiply that across, then what I'll see is that delta V, I'm going to move this over and then bring the C over. So we get the potential difference is equal to charge over C. And so now we can substitute that in here. So we get that the potential difference in the circuit is equal to Q over C1 plus Q over C2. But we said that the charges are the same on both of them, so we can factor that out. So we get the potential difference is equal to Q times 1 over C1 plus 1 over C2. And then if I divide that over, we get this is 1 over C1 plus 1 over C2. And this right here, it looks like that, but it's upside down. because this is equal to the inverse of the capacitance. And this capacitance here, this is the equivalent capacitance. So what I mean by that is that if we imagine that we push these together, that would be this one. We would get one equivalent capacitor. It's not that we actually did it. We didn't create a new one. This is our circuit. But when we do an analysis, a lot of times we'll squeeze it together because we want to find the equivalent. And so my equivalent capacitance, or the capacitance of the entire circuit, of these things together, the inverse of that is equal to the sum of the inverses. And so this is our capacitance for capacitors in capacitance in series. So this happens when we have the same Q. They're one right after another. We have the same Q. We end up with this equation. And looking at it, we could just plug some numbers in. Like, let's suppose that I had a, C1 was, 3 farads. I'm just making up numbers to make it easy. C2 is 4 farads. So we would get an equivalent capacitance of 1 over 3 plus 1 over 4 which would be 7 over 12. But this is not the equivalent capacitance. This is the inverse of that. And this is where students always mess up. We got to flip it. So you can either put it to -1, the power of -1, or you just flip it over. So CEQ is 12 divided by 7, which is equal to 1.71. 1.71. And you can see 1.71 is less than both of these. So that's our second fact of these. So the equivalent capacitance, put it up here, CEQ is less than any of the individual capacitors. Any of the capacitors. It always reduces. Capacitors. So when we hook it up in series, the capacitance of the circuit goes down. So if I just hooked up C1, right, I would have a capacitance of the circuit would be 3. But when I hook up a 4 farad capacitor, it actually reduces the capacitance. I'm going to get less capacitance on here. Okay, so now let's think about in parallel. So in parallel is a little different. So in parallel, what we do is we have like a power source and we hook it up to a plate. But then what we do is we branch off and we hook it up to another plate. So you might be able to see why these are called in parallel, because they're basically like in parallel arms of the circuit. So again, we'll do like C1 and C2, and we'll look at potential difference. So if I have a potential difference from A to B, or A to C, or whatever, I'll just call it B. So if the drop here, if the potential difference, again is like 12 volts or something, then I know I have to go from 12 to 0. So when we come across and go through this path, then we would come back and go this way. We'll talk more about this when we get current involved. And so I know that if I have to go from like 12 to 0 as I pass through this capacitor, what that means is that the potential difference across this capacitor has to be 12. Now what if I didn't go that way? Well, then I would come all the way across and go across this one. But again, I have to go from 12 to 0 because that's a battery. So again, I would get a potential difference of 12 volts. So what we can see is that in parallel, each capacitor has the same potential difference. And it's whatever the battery is. Well, I'll be careful with that because we could add them in series and in parallel. But basically, we'll get the same potential difference in each branch, we could say. Branches are these little pieces of the circuit. Okay, so before we had the same charge and it split the potential difference. Some went to one capacitor, some went to the other one. This one's the opposite. So now what we're going to have is that the charges add up. The battery is going to put out a certain amount of charge, and it's going to be split amongst these two capacitors. So we end up with a split charge. So let's see. So going back, capacitance is Q over V. And if we multiply across, we get C. CV is Q. Just remember V is, it's delta V. So now we can say that the total charge, Q total, is going to be Q1 plus Q2. And then we substitute. So we'll get capacitance 1 times the potential difference plus capacitor 2 times the potential difference. But the potential difference, like we said, is the same. So we can factor that out. So we get QT is going to be delta V times C1 plus C2. Divide that over, you get QT over delta V is equal to C1 plus C2. And this, of course, is capacitance. So in this case, our equivalent capacitance, the total capacitance of the circuit, is just the sum of the two capacitances. The sum of the two. So we just add them up. So if this was 5 farad and this was 2 farad, the total capacitance is 7. So what we see is that in parallel, the total capacitance is greater than any of the individual. Basically, it goes up individual. So parallel, it goes up. In series, it goes down. And then we have these equations. So this is in parallel for calculating the capacitance. Now keep in mind, we can have combinations of these things. And that's what we'll practice a little bit in class, is how to analyze when there's a whole bunch of capacitors in parallel and in series. But that's the general gist.